Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore, and in this lecture series we are discussing about biocontrol system topics, and here the topic is stability of control system. What do you mean by this stability? Why do we need that? What is the necessity of stability in control system? Here we have an answer. And an ability of any given system to attain the steady state condition after passing through transient successfully is called stability. The ability of any given system to attain steady state condition after passing through transient successfully is called stability. Here we have bounded input, bounded output, BIBO stability. A linear time invariant system is said to be stable if it produces a bounded response to a bounded input. Thus, for an unstable system, the response will increase without bounds or will never return to the equilibrium state. So, the response of a first order control system for unit step input, this response has values between 0 and 1, so it is bounded in output. We know that the unit step signal has the value of 1 for all positive values of t including 0, so it is bounded input. Therefore, the first order control system is stable and it gives both input and output are bounded. See here, unit step input response, see the range is 0 to 1. We have t in x-axis and we have the output c of t. It has both bounded input as well as bounded output. Because the values are between 0 and 1, so it is bounded output. Okay, and in this stability we have some classifications, and here first one is absolutely stable system. If the system is stable for all the range of system component values, then it is known as absolutely stable system. The open loop control system is absolutely stable if all the poles of an open loop transfer function present in left half of S plane. Similarly, the closed loop control system is absolutely stable if all the poles of the closed loop transfer function present in the left half of S plane. Okay, and we have conditionally or marginally stable system. If the system is stable for a certain range of system component values, then it is known as conditionally stable system. If the system is stable by producing an output signal with constant amplitude and constant frequency of oscillations for bounded input, then it is known as marginally stable system. The open loop control system is marginally stable if any two poles of the open loop transfer function is present on the imaginary axis. Similarly, the closed loop control system is marginally stable if any two poles of the closed loop transfer function is present on the imaginary axis. See, the general form of transfer function is stability analysis. Here, see, here our formula is g of s, it is equal to y of s, x of s by y of s, it is equal to bm s power m plus bm minus 1 s power m minus 1 plus etc. b1s plus b0. And in the denominator side we have an s power n plus an minus 1 s power n minus 1 plus etc. plus a1s plus a0, which is equal to n of s by d of s. Here n of s equal to bm s power m plus b m minus 1 s power m minus 1 plus etc. plus b1s plus b0, and d of s is equal to an s power n plus an minus 1 s power n minus 1 plus etc. a1 s power 1. a1s means a1 s power 1 plus a0. Here n is your order of the system, n must be greater than or equal to m. And d of s is characteristic polynomial. Here the characteristic equation d of s equal to 0. Here d of s equal to, in general, we denote as an s power n plus an minus 1 s power minus 1 plus etc. plus a1s plus a0, it is equal to 0. See in this diagram, see here in this diagram, the stability is represented. The stable and unstable systems are represented in left half plane and right half plane. See here, stable systems are represented in terms of left half and unstable systems are represented in terms of right half. See, what is this R E of sigma and I M of j omega? What is that? Your R is your real part, I M is your imaginary part. For example, 6 plus 4j means 6 is your real part and 4j is your imaginary part. And we have stable systems in the left half plane and unstable systems in the right half plane. Based on the system condition and based on the stability classification, we can denote the stable and unstable systems in the real and imaginary axis. Yes. Thank you.